This is section 2.9, the dot product. Now, dot product is useful in statics for a number of things, and today we're going to talk about two of those uses. We're going to find the angle between two vectors, and then in the next section we're going to find the projection between or of one vector onto another. Alright, so in this picture we have a couple of vectors. We have this force vector going this way, this force vector going this way. And you may agree, or I hope you can agree, that there is an angle that exists between those two vectors. And what we're going to do is try to find that angle. And maybe you can also observe that that angle is kind of fixed dependent on the distances that you see in the picture. In other words, the magnitude of that force, 400 newtons, this one 250, they could be bigger or smaller and it wouldn't change that angle. The angle is going to be the same. So in this case, the magnitude of the forces don't matter. Only the directions matter in order to find that angle. The way we're going to do this is we're use the dot product. And here's the calculation or the definitions of the dot product. A dot B, in other words, one vector dotted to another vector, is going to be the magnitude of one vector times the magnitude of that other vector times the cosine of the angle between them. Now we can and there's another definition, and A dot B is equal to the magnitude in the x direction of one times the magnitude in the x direction of the other one. And then similarly you multiply the y components and you multiply the z components and add them together. You can kind of see that this is going to be a scalar number when you get done. For example, if ax was 2 and bx was 3, you multiply them together, you get a 6. You don't get 6i in this case. What you're just going to do is just going to get the magnitude. So this is called the scalar product. I guess I could probably write this as the scalar product, and that means that when you get done, all you're getting is a scalar number. Right, so our approach is to define the two vectors and find the Cartesian description of those two vectors and just start multiplying the components. In the end, we'll find out there is an unknown angle, which is the cosine. Alright, so let's see what we can do. First of all, let's define EC. EC goes from, well, let's see what we got. I'm going to go, in this case, I'm going to go -3 in the k direction. I have, let's see, I'm going to go this way in the y direction and this way in the x direction. If you can kind of look at the picture here, this goes 1 meter from the origin here, and this distance is 0.75. So let's define EC. EC, in the I direction, it is 2I minus 0.25J minus 3K. Okay, then let's also find the magnitude. EC mag, again, is going to be equal to the square root of 2 squared plus 0.25 squared, 3 squared, and that's going to be equal to 3.614. Alright, how about ED? ED is just a little bit trickier. We're going to go from E to D, so again we're going to go in this direction, in the k direction. We're going to go this 0.75 in the I direction, and then we're also going to go this far, sorry, that's the j direction, and that one. This distance here is going to be 2. In other words, this right here is 2, and this is going to be the sine component on this side, and this will be the cosine component on that side. So I hope you can see all those pieces. This will be in the I direction going that way. So when you add those together, you get this. You got 2 actually let me move this down just a little bit. So I got 2 cosine 40 in the I direction plus 0.75 plus 2 sine 40 in the j direction minus 3k. Okay, there's our vector description of ED, and I'll just go ahead and do that multiply for you. .036j minus 3k. Alright, what's our magnitude? ED mag is also going to be the square root of the sum of the squares. So I'm just going to give you the answer, 3.936. Okay, now that we have the magnitudes and the vectors, all we have to do is perform the dot products. So I'm going to do both forms and separately here. When you do it, you can do it in one equation if you wish, but I'm going to do it properly and do it with 2 equations and then set them equal to each other. So I'm going to say that EC dot ED is going to be equal to the magnitudes of the x components. So that's going to be 2 times 1.532 that's the magnitude of the x components. We're going to add that together to the y components, so that'd be negative 0.25 times 2.036, and then the y, then the k components or the z components. So we're going to add negative 3 and negative 3. When you multiply all that together, you get this 11.55. Anyway, so there is the answer, the scalar answer of this side of the dot product. Let's do the other side of the dot product. So I'm going to do the similar thing. EC dot ED is going to be the magnitude of the 2 vectors, which is, so again we're using this side now. It's going to be 3.614 times 3.936 cosine of the angle, and then equating those 2 pieces and solving for the angle, you get equating, you'll get theta is equal to the cos minus 1 of 11.55 over 14. I guess I could give you the answer here. I should have done that. 14.22 cos theta. So here, let me complete that. 14.22. Then you can solve that for the angle of 35.7 degrees. So there we have the approach to finding that angle. Alright, so I'd like you to do one. Let's move on to the next example and see if you can do the same thing. So here is another picture. What I'd like you to do is solve for either one. I'll give you the solution. Well, actually, let's look at and see how many angles there might be in this picture. Perhaps you could see that there could be an angle between those vectors. I'll call that theta 1, and it could be an angle between those vectors. I'll call that theta 2. And possibly there you might want to find the angle between those 2 vectors, so I'll call that theta 3. But solve for theta 1 here. I'll show you the answers for both theta 1 and theta 2 after we get done if you need a little extra practice, but solve for theta 1 and pause the video and see what you can find. Okay, here is the solution for theta 1. I'll go ahead and put theta 1 here. I'm going to zoom out just a little bit so you can see the whole picture. But first we defined EC, which is this one, and found the magnitude. Then we find ED and found the magnitude. Then we multiply the magnitudes of the x components, the magnitudes of the y components, the magnitudes of the z components. You get a number. Then we do the magnitude of the vector times the magnitude of the vector times the cosine of theta, and you solve for that. So theta 1 is equal to 56 degrees. And you could have done theta 2 as well. Let's go ahead and I'll just going to show you the answer. If you've done that one, that's another good practice, theta 2. But here we have, I'm not going to get it all on the picture very well here, but theta 2, you solve for, I've already solved for one of those vectors. Let's see, I solved for EC here, right here. So now I just need to solve for EF right there, and I got those pieces of it and multiplying them together, and you can get that for your answer.